Hey everyone, welcome to video 8-1. In this video we're going to be talking about what happens when the perpendicular bisectors of triangles are all able to come together, all the perpendicular bisectors of all three sides. So really only on this page where we're talking about constructing a circumscribed circle, I just want to focus on the vocabulary for you guys because we are going to do this in class. But vocabulary you need to know moving forward in order to use some of the properties that we're going to discover are the following. First of all, if a circle is what we call circumscribed around a polygon, and in this case the polygon we're talking about is obviously a triangle, then what that means is it's a circle that contains all the vertices. In other words, the circle hits on all 3 points of the triangle. Those 3 points are on the circumference, and therefore that's where we get the name circumscribed, okay, drawn around. In the figure, the circle C is circumscribed around triangle XYZ, so this figure right here, his circle C, because C is the center, and here's the circle that goes through X, Y, and Z, and we call this circle C here the circumcircle because it's the circle that goes around the triangle. Then the center of the circumcircle is called the circumcenter, okay? So circumcenter is the vocabulary word we're going to be focusing on the most, but you need to know that it's the center of the circle that hits all 3 points of the triangle. So let's go to page 360 next. So on page 360, we're here at Explain 1, where we're going to be talking about how to prove what is the center of, or the concurrency of a triangle's perpendicular bisectors. So first off, this word concurrency has nothing to do with money, like you see the word currency in there. It has to do with common intersection points. So 3 or more lines are concurrent if they intersect at the same point. So a point of intersection is called the point of concurrency. So where all the 3 things come together in the triangle is going to be a point of concurrency. And we're going to be talking about points of concurrency in these first few sections of Module 8 for lots of different things. We're going to talk about it for our perpendicular bisectors in this section. In the next section, if you look ahead, we're going to be talking about angle bisectors, point of concurrency, and then in section 8.3, we're going to be talking about the points of concurrency for what we know as medians and altitudes. So it's all talking about points of concurrency within a triangle. The one we're going to focus on right now is the circumcenter theorem, and that is the point of concurrency of all of the perpendicular bisectors. And there's a theorem that goes with it, so let's highlight this, put a big star next to it, highlight it with a highlighter marker, whatever you need to do to make sure that you are seeing what's going on here. The perpendicular bisectors of the sides of a triangle intersect at a point that is equidistant from the vertices. So let's underline those words there, equidistant from the vertices. Now what are we looking at? We're looking at this point P right here, okay? That is the point of concurrency of all the perpendicular bisectors. The perpendicular bisectors are these perpendicular segments that you see drawn out to the sides, okay? If we were to continue those lines all the way through those tiny little segments, then you would see the lines all coming together at this point P. But the idea is, remember, that from the previous page we saw that if P is what we call the circumcenter, then all of the points around this circle, all the points of the triangle are on that what we call circumcircle. So if P is the center, I hope you can see it makes sense that PA, PB, and PC are all radii of that circle P, okay? So then the circumcenter says that all 3 of those radii are equal, because that's the definition of a radius, right? So here's what we're going to do. We're going to use some diagrams, and we're going to talk about that anytime we have perpendicular bisectors coming together, they're always going to be equidistant from the vertices or the corners of the triangle. I'm going to envision those radii coming out there. So let's look at example 1. In example 1, we're actually going to prove this theorem that you have that the radii are the same. So it says lines L, M, and N are the perpendicular bisectors of AB, BC, and AC. So here are our lines, and you can see line M cuts through BC, line L cuts through AB, and line N cuts through AC, and these 3 box markings here, you know, means perpendicular. So if those are the perpendicular bisectors, then they are going to be concurrent or intersect at the same point, and I hope you can see how all roads here are crossing at point P. And then what we're being asked to prove is that those radii are congruent, just like in the diagram above here in the circumcenter theorem. So how are we going to prove that? Well, let's read through. P is the intersection of L, M, and N, and so if we can say that point P lies on the something of AB, so point P right here is on the, as you can see, the perpendicular bisector of each one of these sides, so that would be the perpendicular bisector of AB as well. Point P is on that line L, which is the perpendicular bisector of AB. So let's write that in. Perpendicular bisector. And remember what the perpendicular bisector theorem says. You may want to refer back to page 196 really quickly, and that's actually from lesson 4-4, you guys, that talks about the perpendicular bisector theorem. Just take a quick peek back there and you'll see that if any point is on the perpendicular bisector of a segment, then that point is going to be equidistant from the endpoints of that segment. So here we're talking about segment AB, L being the perpendicular bisector, so any point along this line is always going to be equidistant from the endpoints A and B of that segment, and that would have to include point P. So that's why we can say here that PA is equal to PB, and that, again, the reason is the perpendicular bisector theorem. Okay? Oops, I guess I have theorem there twice. Anyway, similarly, point P, remember, is a point of concurrency, so it also lies on the perpendicular bisector of BC. So here we go back to our diagram. Here's BC. Line M is the perpendicular bisector. P is a point on that line, so it is equidistant from B and from C by definition of the perpendicular bisector theorem. So that means that PB is also the same as PC. Well, if PB is the same as PA, then PA, PB, and PC are all equal by our transitive property of equality. Remember, that one means if thing 1 is equal to thing 2 and thing 2 is equal to thing 3, like we have going on here, thing 1 is equal to thing 2, and then thing 2 is equal to thing 3, then all 3 of those things can be set equal to each other. So that's the proof of the circumcenter theorem. And next on page 361, we're going to actually start using it. So I'm here at Explain 2, and we're talking about using the circumcenter theorem that we just talked about on the previous page to find some missing segment lengths in a triangle. So it's really important to make sure that you are reading the information that is given to you in the problem. And so let's do that. KZ, LZ, and MZ, we're told, are the perpendicular bisectors of triangle GHJ. So these 3 segments here are on the big long lines that would cut through them, just like we saw in page 360's diagram there, next to example 1. It's just that they're only showing us the segment that connects to the sides, okay? So just note that the figure is not drawn to scale. I'm going to start using some colors here because I think you can see in parts A and B they give us some different numbers each time. So for part A, I'm going to use blue, and for part B, I'm going to use red, just so you can kind of keep track. Okay, in part A, we are told that ZM is 7, so that's this piece right there. ZJ is 25, and HK is 20. And what we're being asked to find are ZH and HG. So ZH is this piece, and then HG, we want to know what is this piece, okay? So as we reason through this, you can see here that if point Z, if these are all perpendicular bisectors, then Z is the circumcenter. And by definition of the circumcenter theorem, that means that Z is equidistant from all corners or vertices of the triangle. So if that is true, ZG equals ZH equals ZJ. And since we were given ZJ is 25, then that means ZH also has to be 25. So there's my answer to the first one. And then I'm also asked for HG, and HG is this segment right here, this whole entire side. Now remember, what we were told was that these are the perpendicular bisectors. So if ZK is a perpendicular bisector, that means K is the midpoint. And so if K is the midpoint of GH, then HG is twice the length of KH, which we know. So twice 20 is 40. And so our final piece that we needed to find there in part A is 40. I hope that makes sense. Okay, next I'm going to switch colors here for part B. And again, we're still using the same initial conditions, that Z is the circumcenter, or the intersection of all the perpendicular bisectors. This time we are told that ZH is 85. That's this piece right here. And that MZ is 13. So I'm going to take 7 out of the picture, and MZ is now 13. And that HG is 136. This time we know this entire length of the segment is 136. And so what we are asked to find here is that KG and ZJ's values, we need to find those. So K is, remember, by definition of a perpendicular bisector, it is the midpoint of side HG. So that means that KG is equal to half of the length of HG. And so that's equal to half of, we know HG is 136. So KG has to be 68. There's our first value. Then remember, Z by definition is the intersection of the perpendicular bisectors. So Z is the circumcenter of triangle GHJ, and so that means all of those distances out to the vertices are the same. ZG is the same as ZH is the same as ZJ. And since we were given ZH was 85, then ZJ also has to be 85. All right, on the next page, you guys, and I'm on page 362 here, it says in triangle ABC, angle ACB is a right angle. So let's put that information on the diagram. And D is the circumcenter of the triangle. If D is the circumcenter of the triangle, remember it is equidistant to the vertices being A, C, and B. So let's mark what we know there. If it's the circumcenter, all those distances are the same. Now we are told that CD is 6.5. And so if that is true, we want to know what is the length of AB. Well, if it's the circumcenter, then we're going to have 6.5 plus 6.5, you guys, because that's the length of AD, as well as DB, as well as DC, which we were given. So we should be able to easily get 13 there. Okay, for the your turns for you guys today, I want to make sure that in this diagram here, you are, like we talked about, reading very carefully what the information is giving to you. So we're going to have lots of points of concurrency as we move through this Module 8. And so really highlight what it is that you are figuring out point Z is. Make sure that you are going to do question 5 and question 6 is your turn before you move on to the rest of the video.